Okay, so when we talk about organic chemistry, what we're talking about is carbon. Compounds with carbon that are majority made up of carbon. Carbon is an amazing element. It likes to make those 4 bonds. It sits in the middle of the valence electron continuum, and because it likes to make 4 bonds, it's incredibly versatile. It can make all kinds of different structures. I was saying in first period, I liken it to the old Legos. Back when I was a kid and you got the castle kit, it was the old yellow castle kit, you could build anything with those Legos. You could build any of the 3 different castles that they gave you instructions on how to build, but you could literally build anything you wanted out of those Legos. And it seems like these days, Legos are like, you have this particular piece and this particular piece, and you stick them together and you have a spaceship, right? So, and then you can't really use those pieces for anything else unless you get really creative and imaginative, which is fine. We get Legos for Christmas every year. I got Lego flowers from my nephew this year. They're very cool, but I can't use those pieces really for anything other than flowers. So carbon compounds and organic chemistry are more like old school Legos that you can build just about anything, any size, any shape, and then add a bunch of different things onto the ends or to the middle and totally change the properties of the substance. So that's what makes it so exciting. It's also what makes it so super complicated. We have a whole new way of talking about nomenclature that's different from the ionic nomenclature or the covalent nomenclature that you've already learned. So that's what we're going to start with, is a little bit of naming and structures, naming and formula and structures of compounds. So yeah, organic chemistry can be as simple as CH4 methane, which is the main thing that comes out of the gas taps here in the lab and at your house if you have a gas stove or gas heating. But all the way up to super complex molecules like this component of hemoglobin. All of these are contained within the concept of organic chemistry. So we are not going to get too far into this side of organic chemistry. So that's pretty advanced. We'll talk about a few big molecules in the process, but we're going to stick more on this end of the organic chemistry spectrum. Okay, so one of the things that we needed to start with was, how do I identify organic molecules? How do we write their formulas? How do we name them, et cetera? I'm going to just briefly mention that just like in the empirical formula lab that you guys did at the beginning of the year with magnesium oxide, we can use empirical formulas in organic chemistry as well. I'm not going to talk about them anymore until we get back into stoichiometry, but this is something that we do talk about if we have something like C6H12O6, which is the formula for glucose. We can reduce that to its empirical formula CH2O, and that basically just gives the simplest ratio, whereas the molecular formula is going to tell us actually how many atoms are in the molecule. Okay, so they can give us, both of those things can give us information. We can get that information from different kinds of experiments. So we'll get into that more later. So we have our empirical formulas, we have our molecular formulas. We're going to focus on the molecular formulas now. And we're going to add to that a couple of versions of structural formulas. So a structural formula is where you actually draw the structure like a Lewis structure, showing all the bonds and all the different pieces of it. This is a full structural formula. We typically draw it as 90-degree angles because that's the easiest way to show it on a piece of paper, okay? That is not actually what this looks like, and we will next week pull out the model kits so that you can get a better sense of what these molecules actually look like in 3 dimensions, okay? But every single hydrogen is drawn, every single atom is drawn in the structure, okay? There's also something called a condensed structural formula, and I'm sorry that this is so small. I was trying to play with it. This is an old slide, but basically we can shorthand it. Rather than showing all of the bonds, we can turn this molecule here into a condensed structure where we just say, okay, here's a CH3, here's a CH3, here's a carbon and a hydrogen, and here's a OH hydroxyl group. And this is a lot easier and faster to draw than the whole full structural formula. And from there, we can even get to writing a condensed structural formula out that doesn't involve showing any of the bonds at all, but gives us a sense of what the structure is. So here we take our CH3, our CH, which is the next piece. It has an OH off of it, and then we end with another CH3. So we're going to practice writing these for a few molecules. We'll get a little bit more practice on Monday so that you get a sense of what this means. And this is what you're going to see in a lot of your, a lot of the paper 1 questions that I haven't been able to put on your tests because we haven't covered this yet will show organic molecules in a condensed structural formula like this. And you'll have to be able to interpret that. So that's, again, we're going to practice this starting today. And now naming these compounds. Because these compounds can get very big and very complicated, they can have lots of different branches, lots of different functional groups hanging off of them. There's a whole system of nomenclature that is even more complicated than the system of ionic nomenclature, where we have to talk about the transition metals with the Roman numerals and all that kind of stuff. This goes beyond that. The IUPAC, International Union of Pure and Applied Chemistry, they're the ones that decide what things are named. They're the ones who named those last elements in 2015 on the periodic table. Well, they didn't name them, but they approved the naming of those elements. And it's the system of nomenclature, which we're just going to dip our toes into today, is a way of being able to go just the same way you do with an ionic compound, go directly between the name and the formula and the structure, and be able to work between them and be able to know exactly what a compound is just from what the name is. So again, we're going to keep this relatively simple. We're not going to be naming that hemoglobin molecule, but it is going to be more complicated than naming that you've done in the past. One of the ways it's a little bit more complicated is that it uses different prefixes. So you guys are probably familiar with the Greek prefixes that we use when we're talking about binary covalent compounds, like dinitrogen tetroxide means we have 2 nitrogens and 4 oxygens in our compound, and that gives us N2O4. Right? So mono, di, tri, tetra, etc. These should at least be ringing a bell for you. We will also, unfortunately, be using these for part of our organic nomenclature. However, when we talk about the main carbon chains of organic molecules, we use a different set of prefixes. They're different, just the first 4 are different, okay? So instead of mono, for 1 carbon, we use meth. For 2 carbons, it's F instead of di. For 3 carbons, it's prop. And for 4 carbons, it's but. Okay, and I'm going to give you examples of this as we go through today. Everything after that is the same. Pent, hex, hept, oct, non, dec, etc. You're not going to really have to go past hex for our purposes. It does go beyond that. But you don't have to worry about going much further than 6 carbon chain. So you're going to have to know these. And they're going to be, most of the time we're doing organic nomenclature, you're going to use these. But there are going to be certain circumstances where you're also going to use those. So don't forget those while you're learning these, just to make it more fun and more complicated. We won't get to that today, though. Okay, so what I want you to do is look at the short packet that I gave you, the smaller packet, that has a bunch of spaces to write structures and names and things like that. And we're going to start simple. We are going to start with what is known as the alkanes. This is a class of organic molecules that basically have just carbon and hydrogen and only single bonds. Now we can go on to add functional groups to an alkane, but to get started with, we're just going to do pure hydrocarbon molecules. And these are going to be ones where we only have single bonds, no double or triple bonds. Okay. And you'll see that on this sheet, it asks you for molecular formula, which again is how many atoms of each element. The structural formula, which we're going to draw out like a Lewis structure. And then the condensed structural formula, which we're going to write out the way that you would see it in an answer choice on your paper 1 questions. Okay? So the first parts of this are really very simple. The alkanes, the ANE, that is the ending that indicates you have an alkane, and that you only have single bonds. Okay, so when we have methane, the meth means 1 carbon, and the ane means single bonds. So we only have 1 carbon, and we don't have any double or triple bonds. So we have one carbon, and actually I'm going to start with the structural formula and then do the other 2. So we have 1 carbon. When we have an organic molecule, unless it's otherwise specified, everything else is hydrogen. So carbon wants to make 4 bonds, it's going to have 4 hydrogens. And our molecular formula is just going to be CH4. Always put the carbon first. Carbon always goes first. Carbon's always the central atom, and it always goes first. Okay? In the formula. Now, the condensed structural formula, there's nothing to condense here. There's only one little piece of this. This is the smallest organic molecule you can make. So our condensed structural formula is the same as the molecular formula in this case. Okay. So ethane, still all single bonds, but now we've got 2 carbons for F. So we're going to put our 2 carbons together with a single bond between them. And then we're just going to add hydrogens to fill out the rest. So if we count things up here, we've got 2 carbons and 6 hydrogens. Now that's the molecular formula. In this case, the condensed structural formula, we're going to start writing it differently. It's going to give us an idea of what the chain looks like. What are the sequence of parts of the carbon chain? So the way we're going to write a condensed structural formula for ethane is CH3, CH3. So what that's telling us is we have 1 carbon with 3 hydrogens and another carbon with 3 hydrogens, and that's it. Okay? So right now, that's longer than our molecular formula. So you might think, well, how is that condensed? Well, it will be as we get to bigger and bigger molecules. Okay? So propane, 3 carbons, same thing. All single bonds between them in a chain. Hydrogens, wherever there needs to be another bond. Remember, each carbon wants 4 bonds. It's going to get it one way or another. But for the alkanes, all it's going to do is just fill up with hydrogens. So this is going to give us a molecular formula of C3H8. And now our condensed structural formula, CH3, CH2, CH3. Notice that the center one only has 2 hydrogens because it's got 2 bonds. It's got a bond to a carbon on each side. So the ones in the middle are only going to be CH2s. Yes? Right, exactly. So what you're doing is you're painting a picture with this written condensed structural formula of what it would look like. So you should be able to look at a condensed structural formula and say, okay, I've got a methyl group, I've got a CH2, and I've got a methyl group on the end, and that's the whole thing. Okay? Should be able to picture it from looking at the condensed formula. Okay? All right, butane, same thing. Oh, by the way, propane is what you get in the tank if you have a gas grill, right? So that's what's in your tank if you have a propane tank running your gas grill or your camp stove. That's propane. Butane, same thing. Chain of carbons, stick some hydrogens around the outside to make up the 4 bonds. Okay. And we've got C4H10. And now this is where we can start playing around a little bit with our condensed structural formula. So I can write it the same way I did for propane. I can write it thinking 2 and writing 3. CH3, CH2, CH2, CH3. Okay? I could write it like that. But at this point, now I have to write the CH3s on the ends. But now I've got a thing repeating in the middle. And I can address that by putting it in parentheses. So I can write CH3, parentheses, CH2, with a 2 on the outside, saying that I've got 2 of those in a row. And then I've got CH3. And it goes on from there. Yeah. Yeah, they're both considered condensed, but the longer the chain, the more likely you're going to get something like this. Yeah. Okay. So if you look at the molecular formulas down that first column on that first page, you should see a pattern for your alkanes. So we've got CH4, C2H6, C3H8, C4H10. If you had to come up with a formula to represent the relative numbers of carbons and hydrogens in an alkane, how could you write that formula? So if I wanted to write a general formula for the molecular formula for alkanes, I could write CX, and then what is the H going to be for any given number X? Okay, so we're going to have 2X. Is that it? Plus 2. That is the general formula for alkanes. Okay? So, go ahead on that front page, at the bottom, right underneath this butane, there should be a little strip of space there. Go ahead and write the word decane. Write the word decane. I don't want you to draw out the full structural formula, but I want you to give me what's the molecular formula and what would be a condensed structural formula for decane. 10. Yeah. So we got to start by getting the prefix right. How many years are in a decade? 10. So deca is 10. So what's my molecular formula going to be for decane? Vinta? Yep. C10H22. All right. And then what is that condensed structural formula going to look like? What are we going to start with? Okay, yep, we're starting with CH3. Amanda, what comes next? CH what? What comes after the parentheses? Okay. What? Yep. And then what? Yep. So we've got our 2 carbons on the ends, anchoring it, and we've got 8 more carbons in the middle. Yep. Okay, so that's pretty straightforward. Okay, you guys can do pentane and hexane on your own. Oops, I don't. Give me 1 second here. I'm gonna. Thought I had the next bit. There we go. Okay. So the next part is where that's just for a straight chain, just one long continuous chain of carbons without any branches. But we can also have branched chains. We can also, instead of a hydrogen coming off the top or the bottom of the middle of the chain, we can have some more carbons. And so the same terminology that we use for the same prefixes that we use for the length of the chain, a methane, ethane, propane, butane, can also apply to a group of carbons that we can attach somewhere else on the chain. Okay, so if I'm going to attach just one carbon as a branch off somewhere on the chain, I'm going to call it a methyl group. If I've got 2 carbons in my branch, it's an ethyl group. 3 carbons propyl, 4 carbons butyl, etc. You're probably not going to get anything, again, you're not going to have to go above 6 for any of this. And then in the condensed structural formula, those things are going to show up in parentheses to indicate that they are a branch off of the previous carbon in that formula. So what this parentheses with the CH3 here is saying, under number 2 where it says naming alkanes, it's saying that this CH3 is coming off of the previous carbon. So that carbon is connected to, it's connected to this carbon here, it's connected to this carbon here, it's connected to a hydrogen, and then it's connected to that carbon. Those are the 4 things, okay? So you'll notice this is just a CH, not a CH2 anymore, okay? So if we draw this out as a structural formula, the full structural formula, we've got carbon, carbon, carbon. This one that's in parentheses comes out the top, or the bottom, doesn't really matter. You'll see when we do models next week that it doesn't matter. Okay, and then another carbon. And then once we have that skeleton structure here, then we can start adding the hydrogens. So now we've got 3 hydrogens at each of the ends. We've got 3 hydrogens on this methyl group that's coming out as a branch. We've got 2 hydrogens coming out of this carbon that's in the middle of the chain. And we've got 1 hydrogen coming out of this carbon. So that is what the full structural formula is going to look like for this substance. Okay. So sometimes if you just have a straight chain and all you see are CH2s in parentheses, that's just telling you you have a really long chain. But all the rest of the time that you see parentheses, that's telling you that you have something branching off of it. Okay? Now, how are we going to name this? This is where things start to get a little bit complicated. All right? How many total carbons do I have? I've got 5 total carbons, but I'm not calling this a pentane. Because when we name the molecule, we name the longest continuous carbon chain. So excluding the branches. So how many continuous carbons do I have in a single chain here? I've got 4, all right? Now, so this is going to be, what is my root going to be, my root prefix going to be for this? It's going to be a butane, okay? This isn't going to be a butane, but it's going to have some extra stuff on it. So we can't just call it butane because we've got to account for that methyl group on the top, okay? So I'm going to call this methyl butane. Leave yourself a little space in front. Okay, so it's a butane with a methyl group on it, but I also have to indicate where that methyl group is. In this particular case, it doesn't matter, and I'll tell you why in just a second. But I'm going to, in order to be able to tell whoever is reading this name and trying to envision or write the structural formula from it, I'm going to tell them which carbon that branch is coming off of, which means I have to number the carbons in the butane carbon chain. Now, where do I start numbering them? You want to number them so that the branch is on the lowest number. So I could start here and go, this is carbon 1, 2, 3, and 4, and so my branch would come off of 3. But I'm not going to do that because a lower number, it would be better if I start 1 over here. 1, 2, 3, 4. That means my branch is coming off of carbon 2. Okay? So I'm going to number them so that whatever branch is coming off or whatever group is coming off of it, I'm going to have the smallest number. Okay? And so I'm just going to put a 2 in front of here. 2-methylbutane. That tells me that on carbon number 2, I have a methyl group. I have a CH3 group sticking out of carbon number 2 in my 4-carbon chain. Yes? It's a convention. Yeah. Just to keep the numbers as small as possible. Because if I have 18 carbons and I have a chain on the 3rd carbon, it's much easier if I say 3-methyl or 3-propyl or whatever than if I say 15-methyl. Okay? So yeah, we're going to try to minimize the numbers as much as we can. And when you get into really complicated stuff, you start deciding who gets priority over the smallest number, because if you've got a bunch of things coming off of the same chain, then you got to decide where to number it for who gets precedence. But we're not going to worry about that. Yes? So how is this different from this? Right. So it's not. Okay? In this case, it's not. Because we only have 4. And if the branch was on the end, it wouldn't be a branch. It would just be part of the main chain, right? It would just be a pentane. If I took this and I move it over here onto this carbon, it would just be part of the main chain and it would become a 5-carbon chain. If I move it over here, then I just start numbering my carbons from this one. It's exactly the same molecule, okay? Once we get into more complex and longer molecules, it will start mattering. But you're right that in this case it doesn't matter. Also, the other thing that doesn't matter is whether the chain goes straight across the way I've drawn it or up. What if this is carbon 1 up here? This could be carbon 1 up here, and this could be my methyl group. It's exactly the same thing, okay? The way I'm drawing it with the 90-degree angles is not representative of the shape of the molecule. So either way I draw this, I'm going to have a methyl group, either this one or this one, on my second carbon, either way that I start the numbering. And there's a couple times that you'll see questions where they try to trick you, and they try to put a really long chain that looks like it's branching out of the straight chain that is showing, but that's the long chain is actually the longer one. I'll show you an example of that later, okay? So this is going to be 2-methylbutane. Let's do, let me grab one more off of here. Sorry, I thought I had these next two already set. All right. So here's our condensed structural formula. We know that we have a methyl group in here. Oops, oh, darn it. We have a methyl group in here that's coming off of this carbon right there. And then we also have 2 methyl groups coming off of the next carbon. Okay? So we've got 2 branches happening here. So I'm going to start from the left. I've got carbon, single bond, carbon, carbon. I know I have a branch off of here. And then I've got 2 carbons coming off of this guy right here. So that's the skeleton of this structure. So take a look at that and see if that makes sense to you in terms of where the parentheses are. And then I can just add my hydrogens. Now, why did I put this group over here instead of on the bottom? No particular reason. And again, you'll see when we pull the models out that it doesn't really matter. Okay. Things get a little crowded when we start adding multiple branches, and I'm going to show you an even more condensed way, what we call the skeletal formula of showing a compound. I'll do that on Monday. I'm going to go ahead and come back to this one on Monday to give you guys the name. If you want to think about what you think the name should be, feel free to sketch something in your pencil with a pencil. But otherwise, we're going to come back to this. We're going to talk about that, a couple more ways of showing the structure, and a little bit about functional groups.